Hello there, Mr. Sutton bringing you the AB Calculus 6-6 homework answers on motion and position. For this problem, we have a particle moving along the x-axis so that at any time greater than 0, its velocity is given by this function. We're given the position of the particle at time 0, it's 3. We want the position of the particle when its velocity is first equal to 0. So this is a two-step problem. We first need to figure out where this velocity function takes on a value of 0, and we will have a calculator to help us with it if these answer choices make that clear. And then once we've found this time, we have to plug that time into something else to figure out the position. So let's first figure out where velocity is 0. Let me get out my calculator here. So here I've entered my velocity function inside my y equals, and I'm now going to just graph this out and find the zeros. I'm going to use a window from 0 to 4 because my answer choices fall within that range. So we've got 0 to 4, and let me do zoom 0, see what we come up with here. So here's what this graph is looking like. All right, and we want to figure out, again, the time when the velocity is first equal to 0. At least that's the first part of this problem. So although we cross a whole bunch of times, I don't really care about all those extra times. Just this first time velocity equals 0. So let me do second trace and calculate the 0 off of that. So let me move my little spider. Let's see, we're going to go a little bit to the left of my crossing and press enter, and then a little bit to the right. There we go, and enter one more time, and we get a value of 0.655 and some change. Now I'm going to go ahead and store this as a value. I'm going to store this as, let me see here, pressing my stow button. We'll call this A. Actually, let me get out of here first. Now I'll store it. You have to get out of the graph first, and then you can store the answer as alpha A or alpha whatever. So now I can call that up whenever I need it, because I'm going to need to plug this time that I just found into something else to figure out the position of the particle. So I'm kind of thinking ahead here. So here's my graph. I stored this as A, and now let me keep going. Once I have the time, how do I find the position? Well, the position is going to be the initial velocity plus the integral from that velocity to the time we want. So I can say x of a, because that's where we want the position at, the time at which we want the position. That's going to be equal to my position at time 0, which is 3, plus the integral of velocity from 0 to a. And here's where storing that value as a is really going to come in handy now. On this problem, I didn't have to rewrite all this stuff, and on the calculator, I don't have to either. Let me go ahead and calculate that now. So we have 3 plus, let's see, math 9, giving me my integral from 0 to alpha a. There we go. And I'm going to do alpha trace to get my y equals now. This is my velocity I'm plugging into this integral, dx for our differential. And that comes out to about 2.816. So that gives us choice C. For this problem, we have the acceleration of a particle along the x-axis given by this a of t function. At time 0, velocity is -2. For what t value is the velocity 0? So for this one, we need to figure out the velocity function, set it equal to 0, and solve using our calculator on this one. So let's start by getting our velocity function. That'll be the antiderivative of a of t. So we'll use a little diff EQ here to get this. So a of t antiderivative is v of t. And then taking the antiderivative of the right side here, this is 1/2 t squared minus cosine of t plus a c value. Now we have to get our c value. I can get that by plugging in 0 for time and -2 for velocity. So I have -2 equals 1/2 0 squared minus cosine of 0 plus c. This first term is just 0. Here, though, cosine of 0 by itself is 1, so this is -1 plus c. Adding that to the other side, we have a c value of -1. And now plugging that back in, we're just going to set that expression equal to 0. I'm going to do this on the calculator. So here I've entered this left side of the equation in my y equals. I'm going to do a window from 0 to 4 because all my answer choices seem to fall in that range from 0 to 4. And let me do zoom 0 to get the perfect window on this thing. So here we go. And I see that I've got a crossing somewhere between 1 and 2. So let me do second trace and figure out exactly where that's happening. So a little bit to the left for my spider, a little bit to the right for the right bound, enter one more time, and we have 1.478 as the crossing point there. So that's going to be answer choice, if we round off to 2 decimals, answer choice B. On this problem, we have a particle moving on a line with an acceleration given by this a of t function. We have a particle velocity of 5 at time 0. Based off of that, we want the velocity at time 3. So this is basically an FTC problem. To figure out the velocity at time 3, v of 3, we need to take the velocity at time 0, which is 5, and add the total change in velocity from 0 to 3. So that's going to end up being the integral of a of t from 0 to 3. And let me just plug that in the calculator. So I decided to enter this function as y1 just to make it a little bit easier to put in the integral. So quitting out now, I've got 5 plus math 9, that's my integral, from 0 to 3 of alpha trace to get me y1. And I'll do dx here. Enter. Comes out to about 11.710, and that gives us answer choice E. On this problem, we have a particle moving along the x-axis with an acceleration given by the graph here from 0 to 1 for time. And at time 0, they're telling us our velocity is negative 1/2. So based off of that, which of these statements has to be true? So particle passes through x equals 0 for some time between time 0 and time 1. We have a graph of acceleration, and we're making judgments about position. We might be able to if they told us the initial position, but they didn't tell us where this thing was starting. So although our acceleration's positive, I mean, we could try figuring out the velocity, but any of that is not going to help us if we don't know where we're starting. So because we don't know the initial position, choice A, we can't actually conclude that one. Choice B, velocity of the particle is 0 for some time between 0 and 1. So our velocity is initially negative 1/2. And this acceleration curve here, this is adding velocity to this because this is positive acceleration. So the question is, do we add enough velocity to go through 0 on this thing? Well, looking at the area under this curve, we don't know the exact formula for this kind of curvy shape here, but we can draw a triangle that's less than that from here down to here. And this triangle has an area of 1/2 base of 1 times a height of 1, so an area of 1/2. And clearly, we have more empty space underneath the curve. So because we're starting at velocity negative 1/2 and the area under our acceleration curve is more than 1/2, we can say yes, velocity of particle is going to have to be 0 somewhere in between time 0 and 1. Now the other piece of this that we kind of glossed over is we know we have to go through a value of 0 versus just kind of warping from negative 1/2 to some positive value because the velocity function is continuous. How do we know velocity function is continuous for this? Well, the acceleration function is definitely continuous, which means the velocity function is differentiable and thus continuous. So the intermediate value theorem states that because we're starting at negative 1/2 and we're ending at more than 0, because we're adding more than 1/2, we're going to have to go through 0. Looking at some of the other answer choices, in case that wasn't enough to convince you just yet, choice C, velocity of the particle is negative for all values of t between 0 and 1. Well, clearly it isn't. We just proved in part B, or at least answer choice B, that we're adding more than 1/2 to that value. So that means that we're going to end up with at least some positive values for velocity. On the choice D, velocity of the particle is positive for all values. Well, that can't be the case. I mean, we're starting negative and it's a continuous velocity function, so it has to go through other negative numbers to get to positive land. And now then there's choice E, velocity is less than negative 1/2. Well, this is really false. I mean, we started at negative 1/2 and we're adding positive area, so that's going to at least make it more than negative 1/2, even if it never becomes positive at all. So by process of elimination, choice B then. For this problem, we have the velocity of a particle moving on the x-axis given by this velocity formula. If the particle is at x equals 4 at time 0, we want the position at time pi over 2. Well, that's an interesting time, but if you look at the type of function involved, it makes sense. So how do we figure this out? Well, the velocity, or rather the position, at time pi over 2 is going to be equal to the position at time 0, which is 4, plus the integral from 0 to pi over 2 of our velocity function. So this is going to be equal to 4 plus, well, now what's the antiderivative of the velocity function here? So antiderivative of sine is negative cosine, but we have a 2t inside, so we're going to have to divide by that tail of 2. So negative 1/2 cosine of 2t then, evaluated from 0 to pi over 2. So that's going to be 4 plus all of this with pi over 2 plugged in, minus all of this stuff with 0 plugged in. So that's 4 plus, and now this is really cosine of pi, which is going to be, let's see, negative 1, but we have a negative half times that. So that ends up being positive 1/2 for that first bracket there. Over here we have, let's see, cosine of 0, which is 1. That becomes negative 1/2, but this negative outside makes it positive again. So we have 4 plus 1/2 plus another 1/2, which all adds up to 5. Choice D. For this one, we have a particle moving on the x-axis with an acceleration given by negative 4 sine of 2t. If the velocity of the particle at time 0 is going to be 7, and its position is 0, we want the position at time t for any t value. So we want the general formula for x of t. So we're starting with acceleration. We have to get to position. That means we have to go antiderivatives 2 steps. Now, it's really hard to do this with FTC, so we're going to use a diff-EQ approach instead on this one. So I'll start by taking the antiderivative of my acceleration equation up here. Antiderivative of a of t is going to be v of t. And on the right side, antiderivative of sine in general is negative cosine, and we're dividing by 2 because of this 2t inside. So that's going to be positive 2 cosine of 2t plus c1. We'll call it c1 because we're going to have another constant later on. Now to find my actual velocity formula, which I'm going to need if I want my position formula, I'm going to plug in 0 for t and 7 for velocity because of this initial condition here. So we have 7 equals 2 cosine of 2 times 0 plus c1. Cosine of 0 comes out to 1, so that's just 2 plus c1. Subtracting 2 from both sides, we have a c1 value of 5. That means my velocity formula is 2 cosine of 2t plus 5. Great. Let's go ahead now and find the position formula. So that's going to be x of t if I take my antiderivative. And antiderivative of cosine is sine, divided by 2 now because of that 2t inside. So we end up with 2 over 2, or just 1 sine of 2t, plus 5t plus c2. Now we have to find the value of c2 by plugging in our initial condition for position. So we have 0 going in for x over here, and that's with an input t value that's also 0. Sine of 0 is 0, 5 times 0 is 0, so we end up with c2 equals 0, which means x of t really just equals sine of 2t plus 5t plus 0, or just with no plus anything at all. And that ends up being choice A. For this problem, we have a particle going along the x-axis with a velocity given by this rational function here. If our position at time 2 is x equals 1, we want the position at time 4. So position at time 4 is going to be the position at time 2, which is to say 1, plus the integral from 2 to 4 of our velocity function, the change in the x value. So we can just do this on the calculator. I'm going to enter my function in my y1, and then quitting out of there, I've got 1 plus the integral, so math 9, from 2 to 4 of alpha traced, pull up my y1 function, and then dx comes out to 1.353 if we round it off, and that's choice C. For this problem, we're going to be using this table here, which tells us the velocity of some particle moving along the x-axis at various times. And we're told that we have a differentiable function v, and let's see, x is measured in meters, time in seconds. We'll have to include that when we come up with our answers on these problems. And finally, position at time 0 is 7. That'll be important too. But for our first part of the problem, we just need to estimate the acceleration of our particle at 36 seconds. Well, acceleration is the derivative of velocity. We don't know the exact velocity formula, but we can find the average rate of change of velocity to at least estimate the acceleration. So to estimate the acceleration at time 36, I want to find the average rate of change over an interval that includes time 36. Probably the smallest interval is the way to go on this. So I'm going to pick the interval from 32 to 40. So I'll say that the acceleration at 36 is approximately equal to the following. So I'm going to have v of 40 minus v of 32 over 40 minus 32. So that's going to be 7 minus negative 4 over 40 minus 32. And I could stick the units on this since it's all constants at this point and just call it a day. But if you actually calculate it out, this is, let's see, going to be 11 over 8, and that's going to be meters per second squared. On this problem, we want to explain the meaning of the integral from 20 to 40 of v of t dt in the context of this problem. So that's the first part of this. If I'm taking the integral of velocity, that's going to be the total change in position, or the displacement, of our particle, and this is going to be in meters because the velocity was meters per second, so meters, and also include the time interval. So this is from time 20 to time 40 seconds, so from 20 to 40 seconds. So we need each piece of this to get full credit: units, time interval, and what it actually is. Now the next part of the question, use a trapezoidal sum with 3 subintervals to figure out that integral that they just talked about here. So be careful, we're only going from 20 to 40, so these are the only 4 sets of numbers we should be looking at. So I'm going to have, let's see here, base 1 plus base 2, so negative 10 minus 8 over 2 times an interval length of 5. And I'm going to say that this integral of vt dt is approximately equal to, because I'm approximating, I'm not giving the exact value. Next, we're going from, let's see, negative 8 plus negative 4 over 2 times 7 for the height of that trapezoid. And finally, we have negative 4 plus 7 over 2 times 8 for that interval length. And if you put meters on the end of this, you're done. You could actually simplify this if you wanted to. So let's see here. This is going to be negative 9 times 5, so negative 45. This next one, this is going to be negative 6 times 7, so minus 42. And this last one, let's see, 8 divided by 2 is 4. We've got 4 times 3, so that's 12. Adding all this up, this is negative 87 plus 12, so negative 75. And again, that's going to be meters. On this problem, for 0 to 40, must the particle change direction in any of the subintervals indicated by the table? So identify the subinterval and the reasoning. So when we're asking for a change in direction in the particle, we're asking where the velocity changes sign. And we can clearly see, just looking at these numbers here, our velocity is going to change sign somewhere in the interval of 8 to 20, and also, if you look further down, the interval from 32 to 40. Now, we don't know exactly where in those intervals it changes, but clearly, if you're starting positive and ending negative, somewhere in here you changed from positive to negative and vice versa over here. So that means that our particle must change direction on those 2 subintervals. For this last part, suppose our acceleration is positive on the interval 0 to 8. Explain why our position at time 8 has to be greater than 30 meters. So let's talk about the position in general. We're starting at x equals 7 at time 0. So our position at time 8 in general is going to be 7 plus the integral of x prime, or v of t dt, from 0 to 8. Let's talk a little bit more about what this v of t is doing, because we don't have a formula for it, but we do have a table with some values. Now, in general, we can't really assume we know anything about what's going on between time 0 and 8, in between this v value of 3 and v value of 5. But here's the key. Here they said the acceleration is positive. So the velocity's derivative is positive on the interval from 0 to 8. Since we start with a velocity of 3 at time 0, that means the velocity has to be at least 3 across this whole interval. In fact, the acceleration is positive, so it's going to be greater than 3 for most of this interval. But we can say our velocity is greater than or equal to 3 at the very least on the interval from 0 to 8. That means we could rewrite this stuff as x of 8 equals 7 plus integral from 0 to 8 of 3 dt if we wanted to, or we could say that this is greater than or equal to the 7 plus integral from 0 to 8 of 3. Now the integral from 0 to 8 of 3, that's just a rectangle with a base of 8 and a height of 3. So this is essentially 7 plus 24, which is going to give us 31 meters. So this is the lower bound on what our position could be, and that's greater than the 30 meters they talked about in the problem. So we've met our burden of proof by showing this.